Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1880 marks a pivotal moment in the history of physics, cemented by Albert Abraham Michelson's publication concerning the velocity of light. This contribution, more than a mere refinement of existing measurements, stands as a testament to meticulous experimentation, innovative instrumentation, and a burgeoning shift in the scientific understanding of light itself. Its roots lie in a rich tapestry of preceding inquiries, stretching back to the earliest attempts to quantify the seemingly ethereal speed of light. Prior to Michelson's work, numerous scientists grappled with the challenge of measuring this fundamental constant. Old Roma, in the late 17th century, provided one of the earliest estimates by observing discrepancies in the timing of eclipses of Jupiter's moon Io. Subsequent efforts, such as those by Hippolyte Fizeau using a toothed wheel apparatus and Léon Foucault employing a rotating mirror, progressively refined these measurements, pushing the boundaries of experimental precision. However, these earlier methods were often limited by the technology of the time, introducing significant uncertainties into their results. Michelson benefited directly from the conceptual and technical advances of Fizeau and Foucault, using their methodological foundations as a springboard for his own groundbreaking investigations. Specifically, Foucault's rotating mirror technique served as the direct ancestor to Michelson's perfected apparatus. Michelson's 1880 endeavour, conducted while he was a lieutenant in the United States Navy, represented a considerable leap forward in both technique and accuracy. His apparatus, constructed with painstaking precision, utilized an improved rotating mirror system operating over a much greater distance than Foucault's original experiment. The key principle remained the same: a beam of light was directed towards a rotating mirror, reflected to a distant stationary mirror, and then returned to the rotating mirror. During the time the light travelled this round trip, the rotating mirror would have turned by a small angle. By carefully measuring this angle of deflection, and knowing the distance travelled by the light and the speed of the mirror's rotation, the velocity of light could be calculated. The brilliance of Michelson's design lay in its meticulous attention to detail and the minimization of potential sources of error. He implemented sophisticated control systems to maintain a stable rotational speed of the mirror, which was crucial for precise measurements. Furthermore, addressed atmospheric effects through careful calibration and atmospheric monitoring, ensuring greater accuracy than his predecessor. The physical details of the experiment are paramount to appreciating its scientific significance. Michelson established a baseline distance of approximately 600 meters, an order of magnitude improvement over Foucault's setup. This longer path length amplified the angular deflection of the reflected light, thereby improving the sensitivity of the measurement. Furthermore, he employed exceptionally high-quality optical components, meticulously polished to minimize distortions and aberrations in the light beam, allowing for a more focused and easily measurable return reflection. The rotating mirror itself was crafted from a block of specially selected glass, chosen for its extremely uniform density and refractive index. This attention to material properties minimized unwanted optical effects that could compromise the experiment's precision. The rotational speed was precisely controlled by a system utilizing compressed air and a series of carefully calibrated tuning forks. This ensured the mirror's consistent and reliable rotation, crucial for obtaining accurate data. Perhaps one of the most underappreciated aspects of the experiment was the sheer tenacity required to overcome the environmental challenges inherent in such precise measurements. Variations in temperature, air currents, and even vibrations from nearby traffic could introduce subtle errors into the data. Michelson meticulously accounted for these factors, making adjustments and corrections to ensure the integrity of his results. The result of Michelson's 1880 measurements was a value for the velocity of light remarkably close to the currently accepted value. His reported value was 299,910,000 meters per second. This figure, while subsequently refined by Michelson himself and other researchers, represented a significant improvement over existing measurements and solidified his reputation as a master experimentalist. This enhanced precision carried implications beyond just a more accurate value for a fundamental constant. It served as a crucial validation of Maxwell's electromagnetic theory, which predicted a specific relationship between the velocity of light and the electric and magnetic constants. Michelson's measurement substantially bolstered the acceptance and credibility of Maxwell's theory, paving the way for further advancements in our understanding of electromagnetism. The immediate impact of Michelson's 1880 work was profound. It established him as a leading figure in the field of experimental physics, attracting considerable attention from the scientific community. His precise measurement of the velocity of light became a benchmark against which future experiments would be judged. Moreover, The techniques and instrumentation he developed served as inspiration for other researchers seeking to refine their own measurements of fundamental constants. He immediately applied this knowledge. Within the same year, he was made a professor of physics at the Case School of Applied Science in Cleveland, Ohio, which itself was a very new institution at this time, only founded as a recently. Later, Michelson's work on the velocity of light took an even more profound turn with his collaboration with Edward Morley, leading to the famous Michelson-Morley experiment. While the 1880 experiment focused on precisely measuring the velocity of light, the Michelson-Morley experiment, initiated in 1887, sought to detect the presence of a hypothetical medium called the luminiferous ether, through which light was believed to propagate. The experiment was designed to measure the difference in the speed of light travelling in different directions relative to the Earth's motion through the supposed ether. The surprising null result of this experiment, the failure to detect any difference in the speed of light, had a revolutionary impact on physics, ultimately contributing to the development of Einstein's theory of special relativity. While the 1880 experiment laid the groundwork for Michelson's expertise in interferometry and precise measurement, the Michelson-Morley experiment fundamentally challenged the existing understanding of the enduring legacy of Michelson's 1880 work lies not only in the precise value he obtained for the velocity of light but also in the lasting impact it had on experimental physics and the development of fundamental theories. His meticulous approach to experimentation, his innovative instrumentation, and his unwavering pursuit of accuracy set a new standard for scientific inquiry. Furthermore, his work served as a crucial stepping stone towards the revolutionary developments of the 20th century, including the theory of relativity. Physicists such as Hendrik Lorentz and George Fitzgerald directly drew upon the results of the Michelson-Morley experiment, heavily influenced by Michelson's earlier work, to formulate their own theories attempting to reconcile the observed constancy of the speed of light with classical mechanics. Einstein himself acknowledged the profound influence of the Michelson-Morley experiment on his thinking, stating that it was one of the key experimental results that led him to develop his theory of special relativity. The immediate reception of Michelson's 1880 work was largely positive, with the scientific community acknowledging the significant improvement in accuracy he had achieved. However, some critics questioned the theoretical implications of his results, particularly in the context of the ongoing debate surrounding the nature of light and the existence of the ether. Some scientists held on to the belief that light propagated through a medium. Despite the accumulating evidence to the contrary, they proposed various ad hoc explanations to reconcile Michelson's findings with the ether theory, such as the hypothesis that the Earth dragged the ether along with it, rendering the experiment insensitive to the Earth's motion. These alternative explanations, while ultimately proven incorrect, highlight the inherent skepticism and rigorous scrutiny that are hallmarks of scientific progress. Later revisions and deeper understandings built upon Michelson's techniques and findings. Subsequent experiments, employing increasingly sophisticated technologies such as lasers and atomic clocks, have further refined the measurement of the velocity of light, achieving even greater levels of precision. The current accepted value for the speed of light in a vacuum is 299,792,458 meters per second, defined as an exact quantity. This definition arises from the redefinition of the meter in terms of the speed of light and the second, which is based on atomic clock measurements. While Michelson's original measurement has been surpassed in accuracy, his pioneering work remains a testament to the power of careful experimentation and the enduring quest to understand the fundamental constants of nature. It served as a crucial foundation upon which subsequent generations of physicists have built their understanding of light and the universe. Beyond its specific contribution to the measurement of the velocity of light, Michelson's 1880 work exemplifies the importance of precision in scientific experimentation. His meticulous attention to detail, his innovative instrumentation, and his rigorous analysis of potential sources of error set a new standard for experimental physics. This emphasis on precision has had a lasting impact on the field, influencing the design and execution of countless experiments across various scientific disciplines. The legacy extends beyond just physics. The principles of precise measurement and careful error analysis are applicable and essential in fields ranging from chemistry and biology to engineering and medicine. The spirit of Michelson's approach continues to inspire scientists to strive for ever greater accuracy and to rigorously scrutinize their methods and results. Furthermore, Michelson's career trajectory for a young naval officer to a Nobel laureate underscores the value of interdisciplinary thinking and the potential for innovation to emerge from unexpected sources. His background in both science and engineering allowed him to approach the problem of measuring the velocity of light with a unique perspective, combining theoretical knowledge with practical skills. This interdisciplinary approach, characterized by a willingness to draw upon diverse fields of knowledge and expertise, remains a valuable asset in scientific research today, particularly in addressing the complex challenges facing society in areas such as energy, climate change, and public health. In conclusion, Albert Abraham Michelson's 1880 publication on the velocity of light represents a cornerstone in the history of physics. It was not merely a refined measurement, but a pivotal advancement born from meticulous experimentation, innovative instrumentation, and a confluence of preceding scientific endeavours. Its immediate impact, including the validation of Maxwell's electromagnetic theory and the establishment of Michelson as a leading scientific figure, was significant. Its later implications, particularly in the context of the Michelson-Morley experiment and the development of special relativity, were revolutionary. The enduring legacy of this work lies in its contribution to our understanding of light, its emphasis on precision in scientific experimentation, and its inspiration to future generations of scientists. It serves as a potent reminder that scientific progress often results from a convergence of meticulous observation, innovative technique, and the courage to challenge existing paradigms. And perhaps, with a touch of scholarly irony, it underscores how the pursuit of measuring one of the universe's most constant factors ultimately revealed the mutable nature of space and time itself.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.